In this presentation, we'll do a quick walkthrough of the bounce assignment, because some students apparently got lost during the assignment. So a quick summary of what you're actually doing when you're doing this assignment. The goal is that when we have a ball and we numerically integrate it and we end up at a position inside a polygon, that we then simulate a bounce of the side of this polygon. So we see here P is basically the previous position and Q is the newly integrated, which we have by adding the speed times the time step plus the previous position, and this gets us new position. And then we have these two positions and a line in between, and when we cross it with the sides of a polygon, we can detect whether we need to bounce and then calculate the position where we should have been, which we call R. So P, Q are the previous and current position inside, and R is the actually position where we should have been. When we have a shape like this, we can regard the shape as a set of independent lines. So each side of the polygon is defined by 2 points A and B, and a side is simply a vector from A to B. Well, the first thing that we then try to do is we try to find the intersection point between PQ and AB, AB being the side and PQ being the two positions. Therefore, we define two lines, line K and line L, and we define them with the position vector P and the direction vector Q minus P, because Q minus P plus P gives us Q, and this means this is actually the direction vector, the difference between P and Q. And in general, when you want to go from P to Q, you take Q minus P. And similarly, if you want to go from A to B, the vector which does that is B minus A. So we have a direction vector which is Q minus P, and we have a position vector P. And the same for the line L, where we use A as the position vector and B minus A as the direction vector. And this gives us these two equations for the lines, the position vector plus the direction vector. And we see that when we enter 0 for the lambda here, we get position A, so that's when we're here. When we add 1, substitute 1, get a lambda of 1, we get B. So this lambda is a scalar that runs along the line, and when we have an intersection point between 0 and 1, it means that it's an intersection point between A and B, which is an intersection. And similarly for K, we have the mu 0 being P, 1 being Q. Well, finding an intersection between these two lines is simply equating the two equations. So saying L is for which x are the two equations equal, which we've done here. And then we can solve it for lambda and mu, because when you find the lambda and mu, then you have found the position. And whether you enter lambda into this equation or mu into this equation, you in both cases should find the intersection point S. When we find the lambda which is less than 0 or more than 1, or a mu which is less than 0 or more than 1, this means that the line pieces PQ and AB do not cross. Well, to find this is it looks like one equation, but it's actually a set of two equations, because A and B each have two coordinates. So we here have two unknowns and two equations. And we can write that in a matrix like this, where we say we have A times lambda over mu is equal to C. And then we simply call the solver of NumPy to solve this equation. And then we will find this vector lambda comma mu. And once we have found lambda comma mu, we can use either equation to find the actual position of S, and then we have found the intersection point, which means we have now a fifth point for our geometry, which we can then use to calculate the actual bounce. For the bounce, we want to make sure that this triangle that we have here from S, Q, and here the surface AB, this triangle is equal to this triangle. So we see here two line pieces which have an equal length, and Q is the position where we currently are, and R is where we should have been. And we see that these two line pieces have to be equal. The direction to get from Q to R is actually orthogonal to the side of side AB. So that's what we call the normal vector n, which is perpendicular to A and B. You can get the perpendicular vector from A and B by reversing the coordinates of the direction vector which we had. The direction vector was B minus A. Reversing the two coordinates and adding a minus sign to one of them will give us this normal vector. However, depending on whether you put the minus sign on the top or the lower coordinate, we'll get either this direction or we get the other direction. For our bounds, we're interested in this normal vector pointing to the outside, so the direction where we came from. And this means that if we look at the PQ vector and the n vector, that the angle here is actually larger than 90 degrees, which means that the cosine, so it's plus or minus 90 degrees, actually larger than plus 90 degrees or less than minus 90 degrees. And this means that the cosine has to be negative. But if we have a positive cosine, then we probably have the wrong normal vector. We have this vector. So by calculating both vectors which are orthogonal to AB and comparing the dot product, we can make sure that we select the correct normal vector, the one that we need, the one that has a negative dot product with PQ. So it points in the other direction than PQ, and that's actually what it means. When the dot product is negative, it means it points in the other direction. If we have this vector, then we have found this normal vector. This has a certain length. The easiest thing to do is actually to divide it by its length, so we get a units vector, because then the dot product, because with any vector, the dot product and the unit vector gives us the length of the projection. However, we can also get this projection ourselves. So if we take the SQ, the line SQ, calculate the dot product with n, and then divide by the length of n, we get the length of QS times the cosine. So if we divide out the n, we get QS times the cosine. And this length, this is actually the same as this length, and we can see that this is half the distance from Q to R. So if we multiply this by 2, then we get the actual length of QR. And if we multiply this QR times the vector n divided by its length, because we want the length QR but the direction of n, then we need to take the direction n, divide by its length, so we have a length of 1, multiply it by this length, and then we'll get this direction with this length from Q to R, this length in the direction from Q to R. So that's why we have twice here, and that we get twice this length, and then we get the length of QR, which we can then multiply by the vector n divided over n to get the R. And then, so this is the projection of QS on n, twice the QS, the projection of QS on n is the direction, is the length of QR, multiplying it with the vector length 1 in the direction of n, brings us from Q to R. So when we have this vector, we simply add it to Q, and then we find R where we should have been. Basically the same trick is done with the speed. With the speed, we also take the dot product of V on n, we project it on n, we get a negative value because it points in the opposite direction. So we take the absolute value, which was originally missing in the assignment, and you had to add this. You get the length of V projected on n, so that's this length. And then you have to add it twice to the V, and you get in the direction of n, you get the V new. So that's the same trick, basically, what with V and what we did with SQ is the same trick, and this is what you need to do. And then you have found a new position and a new speed. If there's no bound, so if the lambda or mu is actually outside the range 0, 1, this means that there is no bounds, and then we simply return the original Q as the new position and the original speed as the new speed, and we return a bound switch, which is false. And if we have a polygon like this, and we have lambda from 0 to 1 for each side, there is a chance that maybe by rounding errors, the 1 of AB might not be matching fully with the 0 on the other side, and that's why we try to look at a little bit further from the side AB by taking a lambda minus epsilon and the lambda 1 plus epsilon. We actually extend AB a little bit, which we then will still see as a bounce, clip it again to 0 and 1, and this prevents a ball creeping through little holes in the polygon, and in case of a pinball machine, getting our ball inside some shape where it will never escape anymore. And that's what you need to do for the bounce.